Welcome to clickmyproject.com. Now we are going to discuss about our product title is a short channel effect degraded noise margin model for junctionless double gate MOSFET working on sub-threshold CMOS logic gates. Let me see our process abstract. We present a short channel effect degraded noise margin model for junctionless double gate MOSFET working on sub-threshold CMOS logic gate. The device parameters such the thick silicon thickness, thick gate oxide thickness, high doping density of short channel length of servely the degrade the NM due to the serious SCE. By our process the demand ultra low power design the increasingly for all modern Verilog scale integration process application due to the increase in the problem of leakage current, thermal management and reliability. To achieve the ultra power consumption in digital circuits, the sub-threshold current has been used problematic and computing device in our process memory cell. In our process, the power saving in the circuit application require the low and to medium frequency operations. In these applications, energy consumption regions on the hand, the device increasing high package density of ultra large scale integrations has pushed the feature size towards nanometer regions. To extend the scalability CMOS technology in the nanometer regions, short channel effect such as long drain induced bore is the poor sub-threshold process. In our major challenging of the above mentioned problem, incorporating multi-gate device architecture in silicon on insulator technology has minimized SEE. The report of the MOSFET under remarkable simple fabrication process, the conventional junction based transistor. The transistor not the challenge associated with the formations the junctions nanoscale regions. In the process the VLSS circuit based on the CMOS developed sub-threshold current model in equivalent circuit model. Let me see our process flow diagram. In our process we have given the input first to the CMOS design. Input means we give the bit wise what's the clock y zeros or ones. This is the input, and then CMOS design. The CMOS design the complementary metal oxide semiconductor. CMOS is a technology for construction integrated circuits. CMOS technology is also used for several analog circuits such as image sensors, the data converters and highly integrated transceivers for many type of communications. Two important characteristics of CMOS device are high noise immunity and low static power consumption. And then we're going to using the DML and PTL process. It's converted to the split the process for inverter chain and comparator. So first we design the inverter. The inverter process the digital logic, and inverter is a logic gate which implementation logic negations. The inverters is basic building blocks for in the digital electronics, multiplexer, decoder, static machines, and other devices for using the digital device may use inverters. In our inverter circuits output a voltage representation is opposite logic level to its input. The circuit consists of both PMOS and NMOS. The PMOS and NMOS is combination of CMOS inverters, and then we go into the inverter chain. The inverter chain which has the builds a more number of inverters in the circuit. Each inverter is in the design built by CMOS and DLMS logic gate. The inverter chain can be extended or minimized to the n time of the process inverting 1 to up to n type of inverters. The logic of design focus the logical efforts analysis and delay factors. And then we designed the comparator. The comparator is a device that compare the two voltage or currents output of the digital signals. It has been analog input terminals and one binary digital output. Comparator consists of specialized high gain differential amplifiers. They are commonly used in the device that measured and digitalized the analog signals such that analog digital converters. And we using the DLMS gate. The DLMS standard for the dual mode logic gate. It's composed of the digital static logic families. We already discussed the DLMA family is used to delay optimization, path length minimization process, and the DLMA design is having the very simple design. It requires unconventional sizing methodology to achieve good performance. And we go into the BTL. The PTL process is the pass transistor logic. The methodology pass transistor logic describes several logical families used to the design and integrated circuits to reduce the count of the transistor used to make different logic gates by eliminating the transistor and use the switching to post logic level process in our circuits. Let we see our process running processor. We have designed our process CMOS technology in the Tanner EDA tool. We have created the cell for cell 2. So for the code, this is a project, this is a cell for the each and every blocks. We have schematic diagrams, and then whatever the designing we have given, we have designed the using the CMOS, using PMOS and NMOS processes, inverting process. And then how to running the process, and explain that. First we have simulate the setup simulation process. It's very important for that one, the transistor Fourier analysis. We have choose it, and then we setting the tangent Fourier analysis for the falling and rising the waveform process. So we give the stop time for 100 nanosecond and the maximum time set of 10 nanosecond. This process completed, we give OK, and then we just go into the so very important for the one, this is library. We choose the what we have using the library files, generic library files. We choose the same location of the our product designing code. After this, using this process completely, we go into the running the process. They automatically W edit waveform generation is open. We have just invert under the process, explain that. So W edit waveform viewer is open, and now we have input and output the process. Which time I have given input for the this time G have 1 0 to 10 and 10 to 25, like that is off condition, and 25 to 35 is on condition, and then for 35 to 50 is going to off conditions. So this is times of giving the 0 1 0 0 1 0 0 1 0 0 1 0 0. Now this is the input for this signal, and this we get the output for this for 1 0 0 0 0 1. This which time is rising the time for the waveform. At the same time the inverting the process, we get the output for this one cell 2. The same time this time we will be rising the on time, at the same time it will be the off conditions. This 10 to 50 is off condition, the time is rising, inverting the process for 10 to 50 is on condition. This is the process for the inverting process. At the same time the converting process, the both is equivalent to the comparing the process high or low, the whatever the which is gain is maximum differentiated, the comparator will be given the rising time for voltage is comparating clockwise. And then we go into the which this process is gave output for that T space for the. So this is a total timing for 1.18 seconds. We get the maximum output running the time. So it's very important how many time it will take it, and then it gives boundaries lines for the here. Thank you viewing our website.